Hi everyone, so today we're going to be talking about our automobile data. For our project, we explored which characteristics of vehicles resulted in the lowest insurance risk. After working with all the variables and creating different linear regression and CART models, we found three variables that were the most important in contributing to the insurance risk of a car. In our conclusion, we'll provide explanations of these variables and what they mean. First, we have our research abstract and proposal. In this project, we used the automobile dataset from 1985 Ward's Automotive Yearbook. This dataset involved different characteristics of vehicles and their assigned insurance ratings. We explored how these properties can be used to predict the car's insurance ratings. We didn't end up using all of our data because our dataset was pretty small. We did have to remove certain cars from the data when their responses to variables were unique, which meant that there weren't any other cars with that response. We also had to remove an engine location variable since every car we used had this same engine location. However, we did examine every other variable other than those. We made linear regression models and CART models predicting symboline, which represents insurance risk rating. Based off these CART characteristics, we determined which variables were most important to predicting insurance risk. So this is our full research abstract proposal, and we had our main question of different characteristics of cars versus insurance risk, and then we planned to make different linear regression models and then a CART model. And then in our data set, we have about 200 different cars and 26 variables. And the cars cover a lot of different kinds of cars, like economy, standard, and luxury, which makes it really helpful for comparing trends across different brands and styles. And since our data set is so diverse, it can be used for many different types. We personally used insurance risk, but we found another project that focused on price instead. And so it's pretty similar, but we can show how our data set is pretty diverse and how you can use it for a lot of different things. So we had three different types of variables, which was the categorical variable symboline, our normalized losses, which was numeric, and then our last type of variable was all the other variables, which was different characteristics of cars. Some were categorical and some were numerical, but we compared them all against symboline and normalized losses. Overall, our total goal was to uncover which characteristics strongly influence a car's insurance risk, and then also how we can help people and how our information can help insurance companies, but also people buying a car, to talk about car safety and the insurance costs.
Here is our data dictionary page. It basically defines all of our variables. Moving on, we will be talking about data exploration and the tidying of our data. Here we have some links to our sheets, QMDs, and CSV files that are relative to our project. Before we do anything like making models, we need to clean and tidy our data set. This is so our data is consistent, has consistent values that we can easily work with. First, we set up clear names for variables and a data dictionary, as previously shown. This is so we can stay consistent with writing and analyzing our data throughout this project. After we finished preparing our CSV file, we imported it into RStudio so we can manipulate the data. First, we replaced the missing values with NA. This is so RStudio recognizes that these values are empty and not additional text responses. Next, we noticed our data used the actual spelling of numbers rather than the numerical values. This is important because we cannot create accurate, meaningful models without the actual numbers for these specific variables. Because of this, we changed the numbers into numeric ones. Additionally, we changed the type of value in some variables like normalized losses and horsepower from factor to numeric. To test our data out, we created a simple scatter plot with a regression line. Using normalized losses as our response variable, we can see that less highway miles per gallon that a car has, the more risky it is. Lastly, we wrote our dataset to a clean CSV file. This is so we can use it for analyzing. In this next page, we will be focused on creating linear regression models. Before making the models, we need to see the best candidates for creating them. First, we had to determine whether symbolizing or normalized losses had a stronger relationship with the other variables. To do this, we created a grid of graphs, each comparing normalized losses to all of the numeric values. We did the same thing for symboling. We repeated this process with all of the categorical variables. And looking through all these graphs, we decided that symboling had the stronger relationship with the other variables than normalized losses did. Because of this, the rest of our research focuses on symboling as our response variable.
Okay, so in this next part of our project, we'll be looking at linear regression models that we created. So first, what we had to do after loading in our data, we had to remove certain rows of the data set that were having unique values. For example, there was one car that was Jaguar. So when splitting our data into the testing and training data set, it was just causing problems with like comparisons. So we just went ahead and removed those 3 lines. And then here's where we split our data into the training and testing set. We'll create our models using this training set and then compare the models to the testing data set later. And then when we were viewing those promising candidates that we showed earlier, we decided that height, peak RPM, wheelbase, number of doors, number of cylinders, and length looked the most promising just from like viewing them. So we decided to make linear regression models showing each of those, just like height versus sibling. So height resulted in 0.17 R squared value, peak RPM resulted in 0.06, wheelbase was 0.25, number of doors was 0.34, number of cylinders was 0.006, and length was 0.09. So obviously those R squared values are not very high at all, and our goal is to have the highest R squared. So we decided to combine those variables to see how that would work. And with these promising variables, it resulted in a model with a 0.51, which still isn't very high. So after that, we are just going to go through each variable and add it to the model to see how it affects the R squared. And after adding every variable except for 3, except for horsepower, bore, and curb weight, our R squared value increased. So this is just showing after each one, our value increased by a slight amount, except for those 3 variables. And let's go through all these. And after doing this all by hand, this resulted in a model that had an R squared value of 0.8839, which is really high. This is good for what we want our model to be. So after that, we just made a model with all the variables to see how that would do. Besides engine location, as we mentioned earlier, all the cars had the same engine location, so it just doesn't make sense to add that into our model. So this resulted in an R squared value of 0.8859, which is the highest one we've had so far. So this means this model is pretty good. But to prevent it from overfitting the data, we decided to do a stepwise regression to find the lowest AIC score, which like measures the model's goodness of fit to the data. And this resulted, after a lot of different testings, this resulted in a model that had 0.8786 R squared value, which is a little bit lower, but it's still pretty good. And now we know that it has a good AIC value, so this model is pretty good for our research. And the only variables that weren't included were width, curb weight, fuel type, wheel drive, number of cylinders, horsepower, bore, stroke, and price. And that's consistent with what we did earlier with by hand. And then this is just showing the AIC scores compared to the one we did by hand, the one with all variables, and the stepwise regression. The stepwise regression clearly has the lowest AIC score of 179. So we are confirming that this is the best model. And then after this, we just compared our models to the testing data set and the training data set. So this is our model with all the variables compared to the training data set it was created from. So the x-axis here shows the actual variable of symboling from the training set, and then this prediction y-axis shows what the thing is predicting. And as we can see, this one looks pretty good. There's a little bit of variation, but for the most part, it looks pretty good. And then this is it compared to the training or the testing data set. There's a little bit more variability, but for the most part, it's doing pretty good. But then we compared it, we did the same thing with the fitback model. This is the training data set compared to the fitback model, and it's looking pretty good just like the other one, but just slightly better. And then when compared to the testing data set, we can clearly see that this fitback model is better than the model with all variables. And then below here, we just have the output of that fitback model. So this shows the increase or decrease in the symboling variable based on these variables listed on the left here. So symboling ranges from 3 to -3, with -3 being the least risky and 3 being the most risky. So as we can see, like make BMW, if that was true, it would decrease the risk rating, and therefore that applies to all these other ones, whether they're positive or negative.
After we build our first model, which is linear regression model, we're going to build another model that we learned this semester to compare the two models, which is the CART model, classification and regression tree. First, we have some pre-tasks we need to do, like loading libraries and importing dataset, etc. And then we're going to make two CART models. First, we're going to treat symboling as categorical variable, and this is the result from our tree. And it seems like wheelbase, make, and normalized losses are the most three important variables because they were chosen at all the splits, and they appear 2 or 3 times. And for relationship wise with sibling variable, larger wheelbase tend to have a lower risk on cars, and lower normalized losses also tend to have a lower risk on cars. And for brands such as Dodge, Mazda, Nissan, Plymouth, and Toyota also makes car tend to have a lower risk, so they are safer. Those brands are safer to use. This is our summary, and we calculated error for this, and the classification error for the first model was 0.201, which is considered a good model because the error is relatively low. Then we want to optimize our model and get the best model possible. So we're going to tune it twice. First with a large range of CP values from 0.001 to 0.1. We tested around 100 CP values. And then based on the range of cross-validated errors we get, we're going to tune the second time to look a closer into a smaller CP range from 0.5 to 0.7. And this tested around 200 CP values, and our final optimal CP value was 0.0506. We're gonna plot the tree again, but this time not the default CP value, but with the CP value 0.0506 we just found. And then calculate that the classification error. The classification error came out to be 0.264, which is a little bit higher than we because we expected that the better model after tuning should have a lower error. This is our tree, and it looks simpler than the first tree, but and also only 2 of the 3 variables appear, which is wheelbase and make this time, but they have the same pattern relating to symboling variable. After that, we're gonna make our CART models again, but this time with symboling as numeric variable. This is our first tree with the default CP value, and we have again make variable, wheelbase, and normalized losses appear again in the split, but this time there were 2 more variables that were chosen at the splits, which is the numbers of doors and the width of the car. For relationship between these variables with the symboling variable, the first, the wheelbase and normalized losses and brains give the same pattern with the previous 2 models. For the doors, more doors, if the cars have more doors, they tend to have a lower risk. And then if the car is smaller, meaning have a smaller width, they also tend to have a lower risk on cars. Is there some summary for the numeric symboling variable model? We calculated the errors, and the error came out to be 0.182. Then we repeat the same process with tuning 2 times. First with a large range of CP values, and second time with a closer look into the smaller detail CP range. And we plot the graph for CP values and CP cross-validated errors. Then we plot that best tree we think with the new CP values we found, and it appears that they created the same exact tree, because we look back on the models, the trees looking the same, exactly the same, with 9 terminal nodes, and the classification errors also came out to be exact same number. So, and we concluded that using symboling as numeric variables would give a better model because they have a lower classification error. And with all 4 models, we think that wheelbase, make, normalized losses, numbers of doors, and width are the most important variables in predicting the risk of the cars. And this is our conclusion.
Okay. The most important variables that we found for predicting the riskiness of a car are make, wheelbase, and number of doors. We know this because they were variables both our linear regression and our CART models had in common. Number of doors refers to the number of doors a car has. In our CART model, if a car had less than 3 doors, it had a higher symboling score. Additionally, our linear regression model, the more doors a car had, the lower its symboling score would be. This could be due to the fact that sports cars and convertibles are more likely to be 2-doored. Generally, these cars are faster and more dangerous due to their speed.
So the wheelbase of a car is the distance between the centers of both tires. In our models, we see that the closer together the car's wheels are, the more risky it is. Using the slope from the linear regression model, we can see that as symboling goes up, the wheelbase goes down. When we think about this in real-life cars with shorter wheelbases are probably 2-door cars, small sedans, or sports cars. So we can see why those would be more risky than cars with larger wheelbases, which are like large trucks, big SUVs, and vans. And because of their size, those kind of cars tend to be more safer. And additionally, families with children are probably more likely to drive these cars, which makes it more likely to drive safely. And from that, we can see that cars with a larger wheelbase tend to be less risky, which is consistent with our research finding.
And finally, the make variable is also related to the risk of the cars. The make variable represents the brands that manufacture the cars, and it is related to symboling variable because each brand has their own choice of choosing what material to be used and where to be manufactured, as well as choosing their supplier company. Based on the CART model, we found the best one with the tuned CP value. Brands such as Dodge, Plymouth, Toyota, Mazda, and Nissan tend to have a lower symboling value, meaning they are safer to use. And looking back to the linear model, Volkswagen and Saab has positive slopes, which means they are the most risky out of all car brands we have. Chevrolet, Volvo, and again Dodge and Plymouth had negative slopes, which means they are less risky. And so with both types of models, both Dodge and Plymouth were less risky, and which means they should definitely be considered safe to use.
Okay, and then just to summarize that, so cars with 4 doors are less risky than cars with 2 doors. Cars with shorter wheelbases are more risky. Cars with larger wheelbases are less risky. And then cars from brands like Dodge and Plymouth are less risky. So people can use this when purchasing cars to find cars that have the least insurance risk, so their insurance payments will be lower. And yeah, it's just helpful to people who are looking at cars to know these 3 variables are the most important. So yeah, thank you so much.
Thanks.